From a project delivery's perspective, the decision to use analytics comes at the cost of assuming that the hypotheses necessary for it to work are true, and these assumptions introduce risks. If, during implementation, any of these assumptions do not hold true, there will need to be extra work, which increases the cost and time of the implementation. This is a traditional problem of project management, and analytics projects are, from this point of view, software projects with higher risk. To understand why analytics projects has a higher risk than other software projects, we have to understand which extra assumptions analytics systems require. We split these assumptions in two types: intrinsic assumptions, consequence of a methodical, lasting aspect of analytics, and extrinsic assumptions, consequence of a social, transient aspect of analytics. Let's work them out separately. Software can be represented as an input-output system, an operation that receives an input and returns an output. Analytics is no different. Most software makes assumptions about its input, and I will now argue how analytics systems make stronger assumptions about its input. To this end, I first provide an assumption that is common to BI and analytics, invariant data schema, and then describe two strong assumptions made only by analytics: behavior to an expected input and data stationarity. Both make analytics riskier to implement than other systems. A data schema is invariant when each datum has a type, for example it's an integer, that does not change. When the data schema changes, the software almost always requires a code change, or otherwise it will not work as intended. For example, the backend of a website almost always makes this assumption about the database. This assumption is necessary because data types have a strong impact on how a user is expected to have it represented in a browser. BI needs to represent data, and thus it also makes this assumption about input data. Almost any analytics system in production needs this assumption because analytics models that form a core part of analytics systems require specific data types to work as expected. Almost every software aims to be resilient to unexpected input. Achieving this resilience comes with an important assumption: the software's output in case of unexpected input. If a BI tool outputs error, unexpected input, in case of unexpected input, we, humans, can interpret that output in our decision-making process and act accordingly. For example, by providing the best guess that one has without having a BI tool in place. Analytics systems, on the other hand, have a much harder time encapsulating this behavior because they do not rely on a human to weigh in whether the system's output should be trusted or not. We can obviously analyze the decision's usefulness a posteriori and try to improve the system, but this does not change the fact that an analytics system requires strong a priori assumptions about what it should decide in case of unexpected input. Contrary to other software, analytics models make assumptions about the stationarity of the data generating process. A specific summarization of the data that was useful in the past will remain useful in the future. This assumption is very demanding. One example is when the empirical distribution of data changes from normally distributed to skewed. In this situation, an implementation of a previously performant analytics engine will very likely start taking poor decisions. In summary, analytics systems need stronger assumptions about their input and intended output because they bypass the control that is normally done by specialists. These assumptions induce risks to its implementation. Regardless of whether we can mitigate these risks or not, their existence is sufficient to conclude that, all things equal, analytics software projects have a higher risk than BI projects. Analytics shares the same adoption lifecycle of innovations, and this induces many of their hypes and counter-hypes. These are natural consequences of the uncertainty around the value of an innovation and when they should be adopted. The most relevant aspect of this cycle is that analytics is often oversold. While this is a natural process in the life cycle of an innovation, from the value delivery's point of view, it introduces risks, mainly due to misaligned expectations. I have three categories of hypotheses that lead to misaligned expectations. The first is business hypothesis, and it's related to the applicability and valuation of analytics. For example, the decision to use analytics on a use case needs to be based on the true value that analytics can deliver for that use case. The second one is management hypothesis. That's related to the organizational capability to realize value from analytics. For example, does the organization already has the technical knowledge and skill set to deliver analytics projects at scale? The third one is technical hypothesis, and that's related to whether the technology is ready to realize the value that analytics promises in this particular project. This list can be thought as a checklist that can help you questioning the risk-adjusted return on investment of a proposal to use analytics on a given use case.